Hello, welcome to my channel. In this video is the problem number 3 of the constraint motion in the constraint motion concept in the dynamic series that I'm trying to do. So in this problem 3, it looks more complex than the first two problems, but don't worry, we'll dive into it together. Okay, so firstly, the I would like you to understand the point they try to make in the statement here. It says that the determine the expression velocity VA of the card A in terms of velocity VB of cylinder B, but they also said the dimension that they consider positive. So it said like velocity VA of the card A down the incline, meaning that if A go down in this direction, it consider positive value. And it said in terms of the upward velocity VB, meaning that this cyclical B going upward like this, then we consider it positive. So firstly, in every constraint motion with the rope that constrain the motion, we say that the rope does not stretch or compress, therefore the total length of the rope will be constant. Okay, so I already described how the rope will be count, and summation was shown here. Small l plus b plus 2y plus Poulet curves. Now we go to one by one and tell you each uh, definition of each variable here. So first, let's look at the L. Okay, L will be equal to the square root of x square of x powered by 2 plus h powered by 2. So this L will be indicated the length of the rope in the incline that here. Okay, I apologize for my drawing. It's maybe a little bit confusing, but it's safe to say that this inclined L start from here to here is called a small l here, and the x here is a red indicating the red arrow here at x. Okay, so L will be the Pythagoras. Use Pythagoras theorem. We know that inclined length L equal to x squared plus 6 plus h squared under square root. Then we assign the dimension from the upper Poulet to the lower Poulet as y. Then we assign the Poulet from left to right. The dimension will the distance apart from left and right Poulet will be as constant as b. Okay, because throughout this motion, these two Poulet does not move. Okay. So then we assign the angle that act from this perpendicular line and the length of the rope, the rope dimension, the rope angle as theta 1, and this x will be distance parallel to here as x1, and this also another theta, this is L. Okay, so what I try to do here is that I try to imagine if card A is moved to here, then that means the value of L will be shortened, X will be shortened, the angle theta will change as well. So this is what I want to point out. Okay, so come back to the total length of rope equation. So for this, we already know that if we summation L, B, and 2 of the Y, and plus all the small curve of the Poulet, you will get this as a total length of the rope. And if we differentiate it, you get that constant L will be 0. This L substitute here in this blanket will be the derivation under time. Also plus derivation of 2y under time the division with respect to time. Then we will get that if we differentiate it, we get 1 over 2 this x squared plus h squared its power of minus 1 over 2, and then differentiate of the x will be 2x, and differentiate of the x will be x dot. Now you may be wondering why h is not taken into account as variable, because it's constant. Because this line of movement and this pulley in this in this axis will intersect each other, and this h value will always be constant. So that's why it doesn't count as the it doesn't count as a change variable. Okay, then 2y differentiated just turn into 2y dot. Then if we rearrange x dot, we will call 2 minus 2 square root of this bracket divided by x times y dot. So now we're able to derive x dot in term of y dot already. The question asks about expression of the velocity VA, that means the x, okay, in term of y dot. Okay, so you can see that I express x direction as same with the question, but in the case of y, my positive y is downward, but their positive is upward. So that means okay, sorry, here's x, here's VB equal to minus. So that's what I was just mentioned, that I refer y downward as positive, but they refer y upward as positive. So which means VB will be equal to minus y dot, and VA will be equal to VA will be minus x dot. Then with that, sorry, positive x dot, because it's in the same direction here and here, right? So with that being said, finally we get VA equal to 2 square root of x squared plus h squared under x times VB. And that's it, the expression they are in the question looking for. And that's it, the end of this problem. I hope you understand how each equation was derived, and I hope you can help you be able to imagine how to solve this problem. So just a short recap of how the solution step logic is about. So firstly, the question show this position of A being here, have a rope attached to here, and then B being here. So you have to imagine that if A was moved lower or inclined down, inclined up, what would be the relation? What will the rope will behave? In this case, I imagine if A is moving up, that means the rope L should have less angle, or the length of L should be shortened, okay, and then B will move down. Makes sense, right? Now next is to just try to identify which one is a constant, which one is a variable. In this case, like I said, the h here, this time from here to here, is constant because the line of action, the line of motion will always be this, and the line of the pulley that we drag will always be here. So this intersection is always happen at the same point, no matter what length of rope will be. Okay, sorry, no matter what this small l changing. Okay, and another thing is that if h is fixed constant, meaning that x1 will depend on x1 will depend on theta, and L will also depend on theta, which means L, theta, and x depend on each other. If one change, the other one also change. Yes, something like that. But this question and this problem, we don't take into account about the theta because the question doesn't ask about that. Instead, we are concerned about the rho and the x the x value, because this will turn into velocity of x of the card A, and L will be turned into the part of the rope length as well. So thank you so much for listening to this video. I hope to see you again in the next video, and hope we can learn more in the next video. Sorry, this is positive. Okay, I hope we can learn more in the next video about the constraint motion and how can we solve those problems. Thank you so much for watching. See you on the next video.